All right, ladies and gentlemen, welcome back to AP Chemistry with Mr. Kenton. Glad you could join me today. And I'm going to be continuing our lessons within atomic structure and electron configuration by finally getting into electron configurations. The last several videos you've been looking through talked about the quantum mechanical model, and then you moved into learning about the quantum numbers, the different types of orbitals, and even the Pauli exclusion principle of talking about the spin of the electron. So you looked at all these different components, and it's all been leading up to our ability to write and assign locations for all of the electrons within an atom. Okay, and so just starting with a real basic definition, an electron configuration shows us the distribution of all of the electrons in an atom. And when we take a look at this, what we're going to start to see, and as you look to the left there, you've got that representation for P5. And so when you look at an electron configuration, it's always going to consist of the following components. And the first thing that you'll notice, which is kind of highlighted right now, is a number denoting the energy level. So that 4 in front of the P5 is indicating that energy level. That would be our principal quantum number. So in this particular case, that's telling me that it's in the 4th energy level. Okay. Now, as we shift over and we start to look at the letter, that's going to tell us the type of orbital that we're referring to within this configuration. And so if you're thinking back, that P designation means it looks like one of those orbitals that's kind of like a dumbbell, right? So it's in a P orbital, the letter tells us the orbital. And the last piece that we're going to see is that superscript by the letter is going to tell us how many electrons are in that particular orbital. So in this particular case, we're on the 4th energy level. We're looking at a p orbital that has a total of 5 electrons within those p orbitals, okay? And so if we start to even think about where that is on the periodic table, 4p5 would correspond to bromine, right? That would be the final component of bromine's electron configuration, 4p5. I hope that makes sense. Now, there's another way to talk about electron configurations, which is in the form of what we're going to call orbital diagrams. Now, if you think back to the previous videos, we talked about how these orbitals, S, P, D, and F, have varying energies. And so our orbital diagrams are another way to represent those configurations by using boxes, okay? And within this, we're looking there's the electron configuration of lithium. It's 1s2, 2s1. And so each of those boxes represent one orbital, right? The first box represents the 1s orbital, which we can see right here. And then the second box represents the 2s orbital for lithium. The half arrows that are in each of those boxes represent the electrons. So for lithium, it contains 2 electrons in its 1s sublevel, and then there's an additional electron in its 2s sublevel. Now, in order to adhere to some of the rules that we've talked about, the direction of the arrow is going to represent the relative spin of the electron. And if you think back to the Pauli exclusion principle, it communicated that no 2 electrons that are in the same orbital can have the same exact spin. So in that 1s orbital for those 2 electrons, we have one that's up and one that's down to designate that opposite spin. Now, as we're filling in electron configurations and filling in these orbital diagrams, we also have to keep in mind something called HUND'S rule. Now, here's kind of a quote of how you define Hund's rule. It says, for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. Okay, now we need to understand what that word degenerate means. We might hear that word and might think, oh, that has a kind of a negative connotation, but in a chemist's sense, when we're talking about orbital diagrams, degenerate means same energy. And so I just want to draw your attention to the 2p orbitals that are in this particular element's electron configuration. So you've got 1, 2, 3p orbitals that are present. Now, this diagram doesn't show it, but the energies of this p orbital, and this p orbital are the same. They're not different. Okay, and so if we apply this to Hund's rule, what that's communicating is that before you start pairing electrons in the 2p orbital, it's important that each box or each orbital has an electron with the same spin. So if you notice, there are 1, 2, 3 electrons that have an up spin. And then there's 1 with the down spin. The reason why we have 3 with the up spin is because we're trying to maximize the number of electrons with the same spin within degenerate orbitals. We'll be revisiting that soon, so just bear with me here. Now, as it comes to writing electron configurations and the Pauli exclusion principle, we've already seen this, but no 2 electrons in an atom can have the same 4 quantum numbers. They have to have different spins. And so when you look at the example that's been given here, the reason why this configuration is incorrect is because you've got the 2s2, the up-down, but then in this 2p orbital, you've got these 2 electrons right here that are moving in the same direction. You have 2 up spins rather than an up and a down. Whereas over here, you've got your up-down, you've got up-down, up-down, up. And again, we've also adhered to Hund's rule, which we saw previously, where we've maximized the same number of spins. We've got 1, 2, 3 up spins and 1, 2 down spins, right? And so we've got Hund's rule that we need to consider when we're looking at orbital diagrams. We have the Pauli exclusion principle that we need to consider when writing orbital diagrams. Again, looking back at Hund's rule again, the most stable arrangement of electrons in subshells or in sublevels is the one with the greatest number of parallel spins. Put that in layman's terms, place electrons in each orbital one at a time, then go back and place two in them if necessary. Now, to be clear here, what that means, you have to fill up the 1s orbital first. You don't go 1, 2, 3, 4, 5, and then go back to s. No, you fill in the 1s first, then fill in the 2s, and then when you get to the 2p, instead of going up, down, you would go up, 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 and then you would go back through and pair. Right, and this is the electron or the orbital diagram for nitrogen. It has a total of 7 electrons, and that's how we would represent it. So that's that 1s2, 2s2, 2p3. If you look at each of these, it's showing you how it's been correctly done. You got this 1s2, 2s. You got 1s2, 2s2, 2p. You've got 1 downspin, no major issues there. Letter C was incorrect. You've got up, down, then you've got up, down. They either need to be both down or both be up. And so to correct that, they put both of them in the up position. The last principle that we need to consider when it comes to filling an electron configuration, so we've got Hund's rule, which talks about maximizing the same spins. We've got Pauli exclusion principle, which talks about making sure electrons don't have the same spin within the same orbital. And the last piece is off-ball principle. And the off-ball principle states, that as protons are added one by one to the nucleus to build up the elements, electrons are similarly added to the atomic orbitals. And to piggyback off of that, that means that electrons are going to fill lower energy sublevels or subshells first, then they're going to move on to higher energy subshells. And so when we start to look at the periodic table, we do see that it follows a pattern. As you read it from left to right, you're going to see how that gets filled in. And so here we've kind of started off the listing. It's 1s, then 2s. After 2s comes 2p. After 2p is 3s, then 3p, then 4s, then 3d, then 4p, so on and so forth as we move all the way across the periodic table until we get through all of the elements that are on the periodic table. And so the off-ball principle, to summarize, just tells us to fill in the electrons in the lowest energy subshells or the lowest energy orbitals first. Now, looking at the periodic table, I like this graphic because it's going to give you guys something to consider to help you think through what are those numbers and what are those orbitals that are being filled in as I move from left to right. Now, as always, we're going to fill orbitals in increasing order of energy. And so starting at the very top of the periodic table, the top left, the 1s orbital, that's our lowest energy orbital. So we're going to start always in 1s. And as we go across, we fill in the 1s, we go to 2s. We fill up 2s, we go to 2p. We fill up 2p, we move to 3s, then 3p. Then you go to 4s, and this is where things start to change. Once you get to 4s, notice that you have, with the addition of the transition metals, you have a new orbital that gets introduced. The 3d orbital is what's going to be filled in next. So it's going to be 3p, 4s, then 3d, then 4p. Then you go 5s, 4d, 5p. Then you've got 6f. Now we have to be careful here because on our periodic table, if you look at the numbers, it's going to be followed by 4f, then 5d, and then 6p. 7s, 5f, 6d, 7p. I just said a whole lot there. So if you need to rewatch this particular portion, feel free to pause the video, go back, re-listen to that to make sure you really kind of grasp that. Now this periodic table, what it's done is it's shaded in the different blocks on the periodic table to kind of correspond to the different types of orbitals that those elements are going to be found in. That's really useful because it gives you some insight into the last orbital that's being occupied for an element. So the elements that have been labeled in blue, with the exception of helium, right? They're all over here on the left with the exception of helium. Those are a part of the S block elements. And notice that all S block elements end in a configuration that's going to have a maximum of 2 electrons, right? As we move across the periodic table, we enter into our p orbitals. There are 1, 2, 3, 4, 5, 6 elements. Matches up with the fact that we have 3 orbitals that hold 6 electrons. And so these configurations are always going to end in some sort of p, whatever that superscript is going to be for the number of electrons. Once you get to the 4th row and you move into the transition elements, that's where you have your 10 D block elements. And so, again, you would end your configuration with D, insert that superscript. And then the last block is our F block, which is our 14 elements that are there, and they're always going to end with a configuration which is F to some superscript. Hope that makes sense. Now, the fun thing about chemistry, which maybe many of you remember, maybe you don't, but in honors chemistry, you probably were told that there are some irregularities or some anomalies that occur on the periodic table that don't follow the rules like we would expect. And those irregularities or anomalies are going to occur when there are electrons that are able to half-fill S and D orbitals on a given row. So for the scope of our class, this is mostly going to correspond to elements that are in the transition element section on the periodic table. Now, to break that down, what that means, for instance, if I were to ask you to go and write the electron configuration for copper, you would probably give me the bottom example, the noble gas configuration argon 4s2 3d4, because you would be filling in the electron configuration using Pauli exclusion principle, off-ball principle, and HUND'S rule. But what we see, what's observed about the electron configuration for copper, is that it actually adheres to what we've listed here. The electron configuration for copper is going to be the noble gas configuration argon 4s1 3d5. So instead of having a fully filled 4s orbital, we get a partially filled 4s orbital, and we get a partially filled 3d orbital, because that 3d5 fills up exactly half of the orbitals with at least one electron. And so we're maximizing our spins with this configuration, whereas we're not maximizing the spins with this configuration that we would normally predict. Okay. Now, this occurs because, like I said, I just said it, I'll repeat it real quickly. This occurs because the 4s and 3d orbitals are very close in energy. Okay, and so when we start to arrange them in terms of their orbital energies, s and d are really close, and so it's not as difficult for a 4s electron to move into that 3d orbital. Now, these anomalies also occur in the F block, but you will not be required to know any of the anomalies in the F block for the sake of this course or even for the AP exam. Okay, so as we kind of come to a close with this video, kind of a practice that I want you guys to take a look at. You've been able to look at electron configurations. You've been able to look at orbital diagrams. And so now what I want you guys to do is I want you to give me the orbital notation for 10. Okay, so probably need to write out the electron configuration, then go through, do the orbital notation, and then answer the following questions. How many unpaired electrons does 10 have? How many shells are completely filled? So how many of those energy levels for 10 are completely occupied? How many subshells or how many sublevels for 10 have been completely filled? And then how many orbitals for 10 have been completely filled? Now, obviously, you see the answers there, 2, 3, 10, and 24, but pretend like you don't know that those are the answers. Go through, write out the configuration, and try to figure out, did you get those answers? Thank you guys so much for stopping by. I appreciate you guys. I always enjoy sharing this with you. I hope you get a lot out of it, and I look forward to seeing you guys again soon.